Today we are going to have our lesson of chemistry, that is senior 5, and my name is Mugumya Osward. This is lesson 2, meaning that we had another lesson, the first one, so today we shall have a continuation of what we had last time. So our lesson is about nomenclature of complexes, or what we can call naming of complexes in simple language. We are going to just add on what we already have in mind. So this is these are our lesson objectives. 1, by the end of this session we should be able to write the chemical formulas of complexes and coordination compounds. Then 2, we should be able to name the complexes and those coordination compounds. So these are the only 2 objectives we have for this lesson, which look to be simpler when we follow the steps that I will explain in detail. So first of all, when we just started looking at this topic, we looked at ligands. We defined what a ligand is. So before we continue, when we go to naming of complexes, we need to first look at the examples of ligands. When I talk about ligands, we say that we have 2 types of one. We have what we call monodentate, where we say that in such ligands we have only one atom donating the lone pairs of electrons, and we give an example of like water, ammonia, and so on. Then we also talked about polydentate, whereby the ligand has got more than one atom that donates the lone pairs of electrons. And from there we had an example of ethylene diamine. Okay, so here we have just examples. What we should know that ligands, some are anionic. What do we mean when we say anionic? It means that they have a negative charge. So the list we have here, we have the ligands and how their names change whenever they are used in a complex. So when it is just a normal ligand, before being used, it is, for example, the first one, it is azide. Then when it is used to name a complex, or when it is used in the name of a complex, or when it is used within a complex, it changes to azido. If it is a bromide, it changes to bromo. A chloride changes to chloro. Azide, cyanide changes to cyano, and so on. Here we have ammonia, it changes to amine. We have carbon monoxide, changes to carbonyl. Ethylene diamine, or what we can abbreviate as IN, changes to ethylene diamine. If you have water, it changes to aqua. So what we are having on this side, these are the names that are used within a complex when you're naming a complex. In other words, if you have a complex, for example, if I have a complex of maybe copper, if I have an example like this, if I'm to use this, I remember a complex must be in the square bracket, and this one has a charge of 2. So if I'm naming this complex, this water that we have in the brackets, I will not use the word water. Instead, I will use the word aqua. For example, this is a tetra aqua copper 2 ion. Tetra aqua copper 2 ion. So we have changed the word water to aqua. If it was maybe instead here, if we had, let's say, in our brackets, if we have, let's say, ammonia, this is before being used in the complex. So if it was, let's say, ammonia would change the word ammonia, and we use the word amine. That is what we would do. So these are the examples of anionic ligands, the ones with negatively charged. So here From here, these are the ones that we call, these are the ones, some are neutral, some are not, so these ones are combined. But as long as you don't see the charge, if it has no charge, then it is neutral. If it has a charge, then it is either anionic or cationic, as we are going to see. So basically, I wanted to show you that the names change to these. The names do change. Then again, here we are having the neutral ones. Here I sorted some of the examples of neutral ligands. When we talk of the neutral ligands, these are the ones without the charge. They don't have any charge. The charge is 0. So they are negative or positive. So we have ammonia, which changes to amine, like we said. We have water, which changes to aqua. Then hydrogen monoxide, which changes to nitrosil. Then carbon monoxide changes to carbonyl, and so on. So these are the names that we use within a complex, like I said before. And again, these are examples of neutral ligands. So before we go to naming the ligands, naming the complexes, we need to have these ligands in our mind, how they are named, how their names change whenever they're used in complex naming. So to name complexes, we have some rules that we follow. We follow. We look at rule 1, or rule number 1. So in ionic coordination compounds, then of the lesson we shall look at the difference between a coordination compound and also a complex, but they are almost the same. They're almost the same. When I say almost, it doesn't mean that they're the same. So in ionic compound, so this word ionic comes from the word ion. In other words, ionic coordination compound, it can either be cationic or it can be anionic. In other words, the overall charge can either be a positive or a negative. Then a cation is named first, regardless of whether it is a complex or not. So we are saying that a cation is named first regardless of whether it is a complex or not. So in this case, if you look at this coordination compound, we have our cation. Which is this one. So if we are naming, it must be named first. And we are saying regardless of whether it is a complex or not. In other words, this cation here can be a complex. We can have a complex. Here I'm just going to use the general formula. Here we can have a complex. This is the general formula of a complex. So I can have this, whereby we are saying a cation. So by all means, this complex must be a cation, must be positively charged. So I say maybe I can give it a positive charge to show it is positively charged. And then what follows, where it is a complex, it will also be, so meaning that this one will be negatively charged. So we are naming the cation first, regardless of whether it is a complex or not. So we have this example, like I said. So we name the first cation, which is potassium. Remember, we get cations from metals, so we have potassium metal, so which gives us that cation that we're talking about. So this one we call it potassium hexacyanoferrate 2. Potassium hexacyanoferrate 2. Then we can also have this example whereby we are having a cation here. So our emphasis in this first rule is to show how we name the cation first whenever we are naming such ionic coordination compound. So this one becomes sodium tetrabromoferrate 3. Sodium tetrabromoferrate 3. So far we have learned that we name the cation first. So what we should do next is how to come up with such names of tetrabromoferrate 3. How do these ones come in? So we shall keep on looking at one by one. how these ones come in. We can have other examples. Maybe we can have this. I'm trying to use maybe this time let me use like calcium. I'll use calcium, and I have maybe inside I can have like let me also use iron. Yeah, our main aim, like I said, is to show that we first name the cation. So even here we do the same. We can call this one calcium, then we name the complex. Calcium, which is the cation, then we name the complex. What we shouldn't forget is that a complex is always in the square brackets. So whatever we have here in the square bracket is a complex. So now we want to look at how do we name such. In the following rules from rule number 2 and so on. So rule number 2, ligands are named in alphabetical order before the name of the metal atom. Ligands are named in alphabetical order before the name of the metal atom. Then we can say that prefixes are used to indicate the number of a particular ligand. For example, we have words like prefixes like di, which means 2, tri, which means 3. Then we have like tetra, which means 4, penta, which means 5. Just like how we used to name polygons in mathematics. That was, I think, in primary. Pentagon has got 5 sides, triangle has got 3 sides, a rectangle has got 4, and so on. So these words stand for the number of ligands, as we're going to see in some examples. However, for complex ligands, in this case, when we talk of complex ligands, we mean those ligands which are polydentate, those ones which have got more than one atom that can donate the lone pairs of electrons. So in such case, we use the words like bis, which stands for 2, tris, which stands for 3, then tetrakis, which stands for 4, and so on. If there are 5, the word keep on changing. So in case you have a complex ligand or a polydentate ligand, you cease to use the words like di. Instead, you use the words like bis, tris, tetrakis, and so on, as we are going to see. So we have examples. In this case, we are having this. Now we want to look at this first bullet, where we say ligands are named in alphabetical order before the name of the metal atom. Remember, in our first slides, we looked at examples of ligands and their names, how they change their names. In this case, we are having ammonia. We are also having water. But remember, this time they are used in the complex. And we say that once they are used in the complex, their names change. And we say that ammonia, for example, changes from being ammonia to being called amine. And then water changes from being water, then we call it aqua. So what do we mean when we say that this ligand must be named alphabetically? So you need to look for the word which comes first. So between the two, which word comes first? If you check on the word amine and aqua, all of them start with letter A. So they have the same letter. So that one we forego it. We got the second. I hope all of us did alphabetical order in primary. In case you found the first letter as being the same or the second letters are the same, you go move to the third. So here we have the first letters being the same. We move to the third, to the second. So amine now has M, then aqua has Q, which means that amine or M comes before Q. So in this case, amine will be the first. Amine will be the first, followed by aqua. I hope we are together there. Then we got the second bullet. Prefixes are used to indicate the number of particular ligands. So here we have our ammonia, or what we call amine in this case. Now we need to indicate the number of those ligands, the number of amine ligands. How many are they? There are 5. And we say that if there are 5, we use the word penta. Then for water it is 1. So we just leave it the way it is. You can use the word mono, or you can leave it the way it is. So at the end of the day, we shall arrange our ligands alphabetically. So the name becomes penta, which stands for the 5 ligands. Amine, the name of the ligand, which is ammonia, but remember we said it changes to amine. Then aqua, which is our water, nickel to iron. Remember we have said that ligands are named in alphabetical order before the name of the metal atom. So in this case, the metal atom is nickel. We are using nickel. This is the symbol for nickel. Nickel to iron. So this time round we are on arranging and naming the ligands. So after that we shall see how we can determine the metal atom. So we make sure that these ligands are named alphabetically, and we shouldn't confuse this. For example, if someone can say penta, then A. So penta, specifically like penta here, stands for the number of ligands, stands for the number of amine ligands. It's not the name of the ligand, it is just the number, but the name of the ligand is amine. And when we are arranging these ligands, you use their names that they are supposed to use within a complex. So that's why we are using the word amine, not ammonia. And again, we are using the word aqua, not water, because they are already in a complex. Then secondly, we have this complex. So this one has got, here we have water, which are 5. Also have chlorine or chloride, which is 1. So if I have a water, I say this one changes to aqua. This one changes to aqua. And still from the first slides, this is a chloride. We say it changes to chloro. It changes to chloro. So meaning that now we are having A and C, implying that A is first, or comes first before C. So we shall have aqua coming first, followed by chloride, which is now chloro. Then we put the number of ligands of water, which are 5. So prefixes, those are the ones that come first. So it must be first, then followed by chloro alphabetically. So the name will be penta, which stands for the number of water ligands. Aqua, the name of the water ligand. Then chloro, which stands in for the chlorine, for the chloride ligand. Chromium, this is the metal atom. Then for iron. So we shall look at how this 4 comes in as we move on. So each rule matters. So far we have looked at how we can name the cation. We have also looked at how we can arrange the ligands alphabetically, and how to indicate the number of ligands in a given complex. Also, maybe if we had, like, let's say zinc, with also, maybe you can say with ammonia, zinc with ammonia. Maybe we also, here we can put it too. Here we can put maybe bromide, also A2. So A2 here. then of course we have to make it a complex. We have to make it a complex. Then maybe we can give it a charge 2 plus. So this would be, here we have a bromide and also an amine. So meaning that an amine comes before a bromide. This is A, this is B. So we would say there are two diamine, then followed by dibromo, zinc. Then here you have to calculate for the oxidation state. We shall look at how we calculate for the oxidation state. So this should be 4. So it would be diamine, dibromo, zinc, 4 iron, and so on. So we go to rule number 3. Names of anionic ligands end with suffix O. Names of anionic ligands end with suffix O. So what do we mean? Anionic ligands, these are the ones which are negatively charged, like the likes of the chloride. You can see it here, it turns to chloro. An oxide turns to oxo, then hydroxide turns to hydroxo, then a sulfate turns to alphato. If it was maybe a bromide, this one will turn to a bromo, and so maybe we can go back and check. Let's go back and check. There's where we had examples. So like in this example, we are having anionic ligands, or the ones with negative charges. All these ones have negative charges, and you can see all of them end with O. All of them, whenever they are used in a complex, end with O. Bromo, chloro, cyano, fluoro, hydroxo, carbonato. This is an oxalate, turns to oxalato, an oxide turns to oxo. So you can see all of them, they end with O, as long as that ligand is negatively charged, or what we call anionic. So we can continue. We're on rule number 3. Then again, names of neutral ligands remain unchanged. Names of neutral ligands remain unchanged. What do we mean by neutral ligands? Those are the ones without the charge. They are neither anionic or cationic. In other words, they have a 0 charge. However, there are some important exceptions. E.g., we have ammonia, which is named as amine. We have water, which is aqua, in a complex, carbonide, then nitrocyanide. We also looked at the examples in our first slide. Let's check it out and see what we had. So we had this here we had examples of neutral ligands. So we have, this is ammonia, which turns to amine. We have water, aqua, then nitrogen, which comes to dinitrogen, and so on. So this is also a polydentate. This is ethylene diamine. So these are examples of neutral ligands, and we are saying that for them, their names remain. For these names, for them they change the names, unlike others which remain unchanged. So for these ones, the names change, but for others, the names remain unchanged. Okay, so here we are just trying to see how names change, how other names don't change. So we have these exceptions as I've shown you in the other slide. Rule number 4, for cationic ligands. When we talk of cationic ligands, rather complexes, not ligands, for cationic or neutral complexes. That is, we say cationic if the overall charge on the complex is a positive. If the overall charge on the complex is a positive, or we say a neutral complex if the overall charge on the complex is 0. The name of the metal atom is retained. The name of the metal atom is retained. That is, if you find out that the overall charge on that complex is either positive or it is 0 or neutral, so the name of the metal atom is retained. When I talk of the metal atom, here I mean the complex, rather I mean the transition metals which are involved. Remember, we are looking at transition metals, so we are using the transition metal. So the metal atom can be one of the transition metals. For example, if we have copper, if we have this kind of complex, this complex is cationic because the overall charge is a positive. Remember, we had a general formula for these complexes. If I may repeat it, we looked at this in our first lesson. If I may repeat it, it is like this, whereby M stands for the metal atom, M stands for the metal atom, then N stands for the ligands, then N stands for the number of ligands, then Z, this is Z, stands for the overall charge. Here we are saying the charge can be a positive or a minus. If it is none of these, then it is 0 charge. So if I'm to compare these two, the metal atom in this case, it is copper, then the ligand is amine, then N is equal to 4, then Z it is 2 plus. I hope we are together there. So the name of the metal is retained. In other words, copper, which is the metal atom in this case, it will retain its name, which is copper that we know. So our complex would be tetraamine copper 2 iron. So far we have learned how the tetra comes in and how we get the amine. Now we are on how we can name the metal atoms depending on the overall charge of the complex, or depending on the nature of the complex. It can be anionic, that is when it is negatively charged. It can be cationic when it is positively charged, or it can be neutral when it is having a 0 charge. So we should be knowing what really takes place whenever we have different complexes. So you have to look at the complex and you see what you need to apply, which rule do you need to apply, so that we can have a correct name. So our name copper is retained. Another example, if we have such example, we have looked at above when we are looking at arranging ligands alphabetically. It also has an overall charge of positive 3. In other words, here we are having a metal atom which is chromium, so chromium will retain its name. Chromium will retain its name. So this one becomes pentachloro. So it becomes pentachloro aqua chromium 4 iron. So if you have to look at this compound, this complex, if you are to look at it, has a positive charge. So here we are looking at how it is arranged, the overall charge on it, which is positive, so the name is retained. The name is retained. More examples. We have this one for nickel. We also looked at it. It has a positive charge. A net charge is positive, so nickel will retain its name. So this one becomes pentaamine aqua nickel 2 iron. We shall look at how we get the 2, and remember that 2 is the oxidation state or oxidation number of the metal atom. Then also have this. So this one has a 0 charge as long as there is nothing here. As long as there is nothing here, outside here, here, it means that that complex has a 0 charge. we also say that the name of the metal atom is retained. So we call it tetracarbonyl nickel 0. We have to include the oxidation state of the central atom or the metal atom. If it is 0, write it as 0. Don't just leave it like that without writing it. If it is 1, write 1. If it is 2, write 2. Now we go on. Then for anionic complexes, that is when the net charge is a minus, the name of the metal atom ends with suffix At. The name of the metal atom ends with the suffix At. But where the suffix English name sounds awkward, then there we apply the Latin name. For example, we have a ferret, which stands for iron complex. We have argentate, which stands for silver complex. So in cases where we find that we have a complex which has got silver and is negatively charged, or the net charge is negative, silver changes from being silver to argentate. Then cobalt turns to cobaltate, like how we can see in these examples. So we have, for example, this example whereby the overall charge or the net charge is 2 minus. So cobalt is going to change its name from cobalt to cobaltate. So this one becomes tetrachlorocobaltate 2 iron. Tetrachlorocobaltate 2 iron. Remember I said that we shall see how to get what is this number that in the bracket, but I say it is an oxidation state or oxidation number of the metal atom, which is this one in this case. So the net charge is minus, and then now cobalt has changed to cobaltate. We also have that. So this is also having a minus. Net charge is a minus, and we have a metal atom which is iron. We have our ligand, which is, we looked at it, this is cyano, and it is 6. We have 6 of them. So this one will become, when we have 6, it becomes hexacyano. Then iron changes to ferret. Iron changes to ferret. Then we put the oxidation state. This oxidation is 3. So it becomes hexacyanoferrate 3 iron. Rule number 6. The oxidation state of the metal atom in the complex is shown by Roman numerals after the parent metal, or after naming the metal atom. Then a metal complex species is written as one word. So there we have examples. But before we do examples, I want us first remind ourselves of how we can calculate for the oxidation state. Remember, this is something we looked at in our lesson 1, but just to remind maybe the person who has just seen this video before the first one. So for example, if I have a complex, I'm just using a simple complex. We have this complex. So if I have this kind of a complex, remember an oxidation state, it is a charge. It is a charge on a metal atom. So this one, we are looking for the oxidation state of copper. So we call it X because we don't know. Then what is the nature of ammonia? Is it a anionic ligand, cationic, or neutral? So this one is neutral. So we say X, then plus. So when it is neutral, it means it has a 0 charge. Then plus 0, which gives us, which is equal to the overall charge, which is 2. Because it's a positive, we leave it like that. So Ix becomes positive 2. Remember, when you are calculating for the oxidation states, we make sure that we give them the sign. So this is positive 2. So we do the same. If it was a minus, assuming that here we had 2 minus, then it would mean that this would be x plus 0 equaling 2 minus 2. Then you carry out the calculation or the mathematics. So what we should know first is that you first need to know the nature of the ligands that we have. If I use the other example of cobalt, which had a chloride, and here we had a 6, then a 2 minus. So we are looking for cobalt, so it would be x. Remember, the charge on a chloride is minus, it is -1, so it would be -1, then times the number of ligands, or the number of the chloride ions we have 6, so times 6, which gives us the overall charge. Now it is a minus, so it would be minus 2. So this would be x. Here we have in the brackets -1 times 6, it gives us minus 6. Minus 6 plus x. Here we shall be having a positive and a minus, which gives us a minus. So this would be -6, which gives us minus 2. If we go this side, so this one becomes x, which is equal to minus 2. When -6 to cross the equal sign, it becomes a positive, so positive 6. So our x is equal to positive 4. So that is how we calculate for the oxidation state. Like I said, we have the details in our first lesson. So having looked at the rules, this is an exercise, or what we can call review questions. So from here, you just need to check out yourself and see how to name this. Maybe I can help like in this example, this one. There is where we're naming like, if I separate this and I put this is silver, this is silver, I put here, I put this, I'm looking at this, that complex, or that coordination compound. So if I charge it, this one becomes here we have it too. It becomes diamine silver 1 ion, because of being charged. Just like how we name this one, we call it chloride ion because it is charged. But this one we call it chlorine because it is not charged. So even our complex, we are calling it diamine silver 1 ion. But in case you have the ion placed there, like how we have this. So where we have this ion, now we have the chloride ion. Not so? So if I'm naming, I'm going to name the complex, remember the one in the square bracket, then followed by the name of that ion, So this one will become diamine silver 1 chloride. So instead of putting the ion, I put the name of the ion. And in the same sense, we can also get to know the overall charge on the complex. How do we know? We look at the kind of the ion we have. Or the kind, normally these are radicals, which are always negative. Most of them radicals, all of them are, I think all of them are negative. So we look at the kind of the ion that we have. If it is negatively charged, then automatically the complex would be positively charged. In other words, the overall charge or the net charge on the complex is a positive. After knowing that the overall charge on the complex is positive, then it tells a lot. Here you know that the name of the metal atom in that complex won't change. And if it doesn't change, then it helps you in naming the whole compound. So for the case of in rule number 1, we say that if you have a cation, it is named first. If you have a cation, it is named first. And if you have an anion, it is named last. If you have an anion, it is named last. I hope we are together there. A cation is named first. An anion is named last. So like how we have this. So even in this one, the sulfate ion or the sulfate must be named last, because it is an anion. And from here you can also tell which charge do we have on the complex by just looking at this one. So you must be knowing the valences. Let me use the word valences. You must be knowing the valences of the anions. And to simplify it, the anions this time, the ones we normally use, most of them are radicals, and all of us, we looked at radicals in our lower classes. That was on the ordinary level. So it tells, even when you have a cation, like in this case, even when you have a cation, we know that a cation is positively charged. A cation is positively charged. So if the cation is positively charged, automatically it means that the complex would be negatively charged, because these are ionic compounds. It must be a cation bonding with an anion. So we are not having covalent coordination compounds, we are having only ionic compounds. And how do you tell the valency or the identity charge on the complex? For example, if I have this kind of compound, coordination compound, if I have this, how do I tell the charge? Maybe we can give this one 6. How do I tell the charge? So I can tell the charge. First of all, I need to first identify, is it a minus or a positive? Here we are having a cation. Automatically we say this would be positively charged, and if it is positively charged, then this one will be negatively charged. Then how do I tell the overall charge? So the overall charge will depend on the number that is here, that is on the cation. If it is K4, like we have there, it means that the overall charge on the complex would be 4 minus. If it is maybe K3, then the overall charge would be 3 minus. If it is maybe Na, just Na, it means that the overall charge on the complex is minus 1. I hope I'm clear there. It's like how we were making writing the chemical formulas in our lower classes. For example, if I had A and B, elements A and B, this one has a valence of 2, and also this one has a valence of maybe 3. Then we switch. So it means that the 3 will come on A, the 3 will come on A, then the 3 will be here, then the B will be having 2. So we can apply the same knowledge here. Maybe let me change the color there. So we can call our cation A, then we can call our complex B. So mean that this 4 came from B, and here we're supposed to be having 1, but remember, don't write 1. So the 1 came from the cation. So the same thing is applied when we have an anion at the end. An anion at the end. The number on the anion is the overall charge on the complex. Like here, if you had look at this example here, if you had look at that example, here we are having a complex, here we have a 2, then here we have a sulfate. And we are aware that a sulfate, it is written like this, sulfate ion. It is written like this. So this is its charge, which is minus. Remember, I said that as long as we have an anion at the end, then automatically the complex would be a positive, would be having a positive charge. So it means that this 2, it is the one which is here. And if we had a value, a charge here which is more than 1, then this one would be in a brackets. For example, it would be maybe we can put a 2. If it was like a 3, it would be like this. It would be like this, implying that the 3 came from here. So yeah, I'm just giving you the hint on how to go through these numbers. So what we should do here, we have instructions. So since we are playing a video, you have to pause the video, then you copy down these examples or the exercises, then you send to a Google Classroom, and we provided a class code. In case you don't know how to use the Google Classroom, we provided, there is a link in the description that takes you to our Google, or to my Google Classroom. So the link is provided in the description. So I thank you all. We meet in the next lesson. These are my contacts. This is my number, 0705 900 414, which also happens to be on WhatsApp. In case you want to email me, this is my email address. Thank you all.